Welcome to Differentiation. If coordinate geometry is about straight lines with a constant slope, calculus is the mathematics of continuous change. In this unit, you will move from calculating an average rate of change over a wide interval to finding the exact instantaneous gradient at a single specific point on a curve. This is arguably the most powerful analytical tool in pure Mathematics 1. It bridges abstract algebra with geometric reality, and mastering it is absolutely non-negotiable for an A-star candidate. We begin by asking how to measure steepness when it is constantly changing. You will learn to approximate the gradient of a curve by drawing a sequence of chords. As the points move closer and closer together, that chord eventually becomes a perfect tangent. Using the formal mathematical mechanism of limits, you will derive the exact gradient function from first principles. This is a classic, high-value show that question in Paper 1, testing your algebraic rigor.
Calculating limits every single time is slow, so you will quickly move to the algebraic engine of this unit. To differentiate any power of x, you simply multiply by the power and then reduce the power by 1. You will apply this rule to polynomials, fractions, and surds, the later marks. Once you have the gradient function, you will bridge calculus back to coordinate geometry. You will find the exact linear equations of straight lines that just touch the curve, known as tangents, or cut perfectly perpendicular to it, known as normals. Remember, examiners expect you to immediately use the negative reciprocal to find the gradient of a normal, forming the foundation for complex intersection problems.
Next, you will analyze the shape of the curve itself. You will use the sign of your first derivative to prove exactly where a function is sloping upwards or downwards. Then, you will differentiate a second time. The second derivative tells you the rate of change of the gradient itself, revealing the underlying curvature of the graph and preparing you for advanced curve sketching.
Where does a curve perfectly flatten out? You will locate stationary points by setting the gradient to 0 and mathematically prove whether they are maximum peaks, minimum troughs, or points of inflection. This is the exact mechanism you will use to solve heavy-hitting practical problems, such as maximizing the volume of a container or minimizing the cost of manufacturing materials.
Finally, we bring time into the equation. If one variable changes over time, how fast does a related variable change? You will use the chain rule to connect these rates of change. Whether it is an expanding circle or a draining cylinder, you must explicitly state this algebraic relationship before substituting any numerical values. This topic is the ultimate discriminator for top grades in the exam.
To sum up, in this unit, you will derive gradients from first principles, differentiate powers of x algebraically, and find linear equations of tangents and normals. You will classify stationary points to optimize real-world models and solve connected rates of change over time.